Hello everyone. Welcome to a new lecture in the series of Deep Learning for Control. So far in this lecture series, we were focusing on static models and learning static models from both labeled and unlabeled datasets. As we have discussed in the lecture series, static models captures the static or steady state behavior of the system and are suitable for identifying the optimal steady state operating points, which is the real-time optimization problem, and can also be used for soft sensor applications where the objective is to identify relationships amongst the variables in the dataset. However, when it comes to control design, we need to know how the control input is going to affect the system output. In other words, we need to know the consequence of choosing this control action. For this, we need dynamic models which relates past to present or present to future. And in this lecture, we will discuss one of the most popular dynamic models using neural network, which are recurrent neural networks. And also we discuss its application in control. Here is the overview of this lecture. We will start with a brief introduction to recurrent neural network or RNN. Also, we discuss the different variants of RNN. Then we move on to RNN-based data-driven MPC. In general, recurrent neural networks are characterized by recurrent connections, which are also feedback connections. Can be shown as this figure 1. This is one of the most simple version of the recurrent neural network. Here we have a recurrent connection from the output layer, and this particular structure can be used for representing nonlinear system in input-output form as in equation 1, where we have yk plus 1 equal to a function of yk and uk. We can use RNNs as in equation 2 to approximate this model, where fnn will be an approximation of the function f. Yk plus 1 hat is the output predicted using the RNN model, which will be an approximation of yk plus 1. And theta f contains all the parameters, which consist of the weights and biases of all the layers in the neural network. We can select the RNN function as a deep neural network model containing L layers, and each layer can be represented as a composite function as in equation 4. Let's consider the input and output data is available, which can be represented as in equation 5, where we have the UD is containing all the input training data, which consists of U0 till UD minus 1. We have D samples of the input vectors. Now, the predicted output using RNN can be computed as in equation 6, where YD hat denotes the predicted output sequence, which consists of Y0, which is available. Then applying the RNN model, we can compute Y1 hat as fnn of Y0, U0. Similarly, Y2 hat will be fnn of Y1 hat and U1, where we can substitute for Y1 hat from this equation. By applying this repeatedly, we obtain YD minus 1 hat as in this equation. This we can represent as a nonlinear function of the parameter theta f. The prediction error for RNN can be defined as in equation 7, where the prediction error contains error between the actual output and the predicted output, which is summed across all the samples. And this is also equal to the Frobenius norm of the difference between the actual output matrix YD and the predicted output matrix YD hat. Then in the RNN training, our objective is to find the optimal value of the parameter vector theta f, which minimizes the loss function. Popular variants of RNN are the long short-term memory or LSTM network, in which we can have the length of the memory or like the history in the model can be adjusted, which provides a short-term memory to RNN to deal with the vanishing gradient problem. And we can also have gated recurrent neural network or GRU, which is a modification of LSTM. Next, we move on to RNN-based data-driven NMPC, in which we use the steady-state condition to find the reference points for the MPC, where in steady state we can have yk plus 1 equal to yk equal to yr in the case of an output regulation problem. Here, if we are computing yk plus 1 using the RNN model, we will be having yr minus fnn of yr ur equal to 0. Now, by solving this equation, we can find the control reference value ur corresponding to the output reference yr. In general, for MPC, we normally assumes the output reference or yr is available, and by solving this equation, we can find the reference for control. Then using YR and UR, we can find the output reference over the prediction horizon, which is denoted by capital YR, which contains the output reference over the time instance. and also the control reference UR, which containing all the reference values obtained from solving this equation. UK will contains the control input sequence, which contains the next n values of the control inputs. And this is the summation of the cost over the next n instance, which is represented as in this equation. And this defines the constraints. The derivation of this problem is there in the lecture for data-driven MPC, and the link for this lecture is given in the description. In general, for RNN-based data-driven MPC, the algorithm can be summarized as in this slide. We have the available data set consists of the input data sequence UD and the output data sequence YD. And we have to select the number of layers in the RNN and also the each neurons in the hidden layers. Then by initializing the parameters according to the selector structure, we can find the optimal parameters by solving the RNN training problem. Then for the MPC, we have to select the prediction horizon or capital N and the output reference or YR and the weighting matrices for the output and control. And using these weighting matrices, we can construct the block diagonal matrices QY and RU for the cost function. And using that, we can define the cost function as in the previous slide. And we can also solve the control reference UR by solving the steady state condition as in the previous slide. Once we know the control reference and output reference, we can define the output reference sequence YR and the control reference sequence UR. And then we can solve the optimal control sequence UK star by solving the optimization problem in the previous slide. We apply only the first element of the control sequence, which is denoted by UK given K. And this will be applied to the system at the current instant. And this will repeat for each time instant until the end of the simulation time. Now we can move on to a numerical example for illustrating the RNN and its application in MPC. So here we consider a second order CSTR system involving an exothermic reaction in which a liquid denoted by A is converted into a liquid denoted by B. Here the CSTR can be modeled as a second order system with dynamic variables as the reactor concentration and the reactor temperature. In equation 13, we can have a state space model of the CSTR system, which is containing two state variables as we can observe here, where x1 is the reactor concentration and x2 is the reactor temperature. We consider the output as x2, and here we added some noise, which is denoted by Vk. And the system parameters are chosen as in equation 14, and the simulation parameters are chosen as in equation 15. Here we can have the training input and training output, where the red color shows the actual output for the CSTR system, and the green color shows the output predicted by the RNN model. And it can be observed that the RNN model is able to predict the output well. And the figure B shows the output response with an MPC based on RNN model, where the green color shows the reference values and the output with the MPC is shown in red color, where we can see that the output is able to follow the reference. And the corresponding control input is shown in figure C, which satisfies the constraints. This means that the RNN model can sufficiently capture the dynamic behavior in the system, and it can use it for solving MPC problem. The MATLAB codes for this numerical example can be downloaded from the link given in the description. That leads us to the end of this lecture. Thanks for watching.